For coming, and please join me in welcoming Douglas McKee and Mark Bereza.
Thank you, and welcome. We're really excited to be here. We're glad you could come see our talk today. We're going to be talking about a 0-day that we discovered. We're going to walk through our vulnerability research process, our exploitation process, and post-exploitation, and hopefully have some really cool demos for you at the end. So first off, who are the two crazy idiots standing in front of you? My name's Doug McKee. I'm a security researcher for McAfee's Advanced Threat Research team. I've got a little over 8 years of experience in vuln research and pen testing.
And I'm Mark Bereza. I have a little over 8 months of experience in vulnerability research and pen testing.
That's great. So first off, most importantly, what are we here to talk about today? We're going to talk about an ICS system produced by a company called Delta Controls. They refer to it as their IntelliBus Manager. And what this is it's called a building controller. It's used to manage systems in a commercial building, things like HVAC, lighting, pressure rooms, etc. And important thing to note is that this device uses a networking protocol called BACnet. That's largely how it manages these devices. BACnet stands for Building Automation Control Network. And I also want to highlight that this is not specific to Delta Systems. This is an industry-wide used protocol. It also has a little bit of router capability built into it, which I'll touch on here a little bit later. And before I go any further, I often get the question, how do you pick your targets, or why did you pick this target? Generally at ATR, we try to pick targets that can have a very high impact as if they were compromised. Obviously, there's a lot of critical systems that fall into that. And this happened to be one that we were able to obtain. And also, something of interest is the fact that it uses the BACnet protocol, therefore it's network accessible. So let me take a moment to explain to you how this works in the real world before we jump into hacking this device. So what you see in front of you is we have a wiring diagram of one of these devices, potentially for an HVAC system. So you have the Delta controller, which talks over a CAN bus to something called modules. At the highest level, these modules take inputs and uses it to control outputs. So that each device is programmed differently from the installer, and depending on the state of those inputs, it changes those outputs. So in the wiring diagram in front of you, assuming it's an HVAC system, depending on the temperature, it'll do something like turn on or off a boiler, turn on and off a pump, etc., etc. And this is just one example. It's used across industries for multiple things, which we'll get back to here momentarily. So understanding this, how do we start looking for bugs, or where do we start looking for vuln research? Well, as I said, one of the most important things for us from attack vector is we like the fact that it's network accessible. So in front of you can see an Nmap scan of the fact that it uses the BACnet protocol. So now we know what direction we want to attack it from. We're going to do a network attack on this, hopefully. Well, what else do we need? It'd be really useful to have the software. Well, lucky for us, the developers left UART headers on the board, which was completely unauthenticated root access to the system. This made it simple for us to pull off the firmware. So if we look at that firmware for a moment, a couple important things to note is one, there was no ASLR and NX was enabled. And also, it was quickly able to see that symbols were left into the program. This will become extremely useful, and I will reference this multiple times throughout this presentation. So we want to use a network attack vector. So what does that mean? Well, we're going to start with fuzzing, like everybody else. So we decided to use a commercial fuzzer called Defensix. This fuzzer has a built-in module for a BACnet server. We weren't quite using a BACnet server, but because of the router protocol, or the routerness of the device, it had a lot of similar attributes. And one of that is the BACnet protocol uses broadcast traffic pretty frequently. So we used this fuzzer as a starting point and started to fuzz the device. This is one of those packets that you see on the screen that the fuzzer chose to use as a test case. A couple things I'll highlight real quickly. Besides the fact that it's a broadcast packet, the fuzzer here is sending about 8,000 bytes in what's called the BLVC layer, or the BACnet layer of the packet. You can even see that Wireshark is telling you that this layer is really only supposed to be a maximum of 1,476 bytes. I think it's pretty easy to see here that the fuzzer is trying to look for a buffer overflow attack. So we fire up Defensix, we run this test case, and after a few minutes, we see this on the UART screen. Quite simply, what you see is that it's the core dumping and the system's rebooting. Now, I'm a little bit of a pessimist when it comes to vulnerability research, so I never actually believe I found something the first time. And so I run the Defensix at least 2 or 3 more times. And for your amusement, I took a picture of Mark's face once we were running the fuzzer, because this is pretty much what it looked like. And he got excited because we had a reproducible crash. Ironically, though, I went back to that packet that I showed you on the previous screen, and I sent just that packet to the device. Interestingly enough, the device did not crash. Well, I sent that packet twice, and the device still did not crash. Through a lot of trial and error, I actually discovered that it took 97 packets to crash this device. And I'll touch on this here momentarily. But after discovering it took 97 packets, I was able to do it repeatedly. So that meant it was time to investigate further. Well, as you saw, the system could produce a core dump. So let's take a look at that core dump as a first place to start to try to figure out where to move on. Obviously, we have a seg fault here. That makes a lot of sense. The device crashed. But what can we learn about that looking at the registers? Well, let's start with the R0 register. For those of you that haven't fallen asleep yet, you might notice some similarity in what's in the R0 register to the packet of which Defensix decided to send to the system. There's a lot of 22s or ASCII quotation marks. That's interesting. We know that that's network data. If we keep thinking about network data and we look forward at R3 and R8, R3 has the value 81 in it. For those of you that were smart enough not to read the BACnet RFC, you wouldn't know that 81 is the first byte sent in all BACnet packets. This indicates the BLVC layer. Again, this indicates that there's some networking data in the system. And if we take a look at R8 and we account for the Indians inside the computer, we know that this is 47808 or the source or destination port. So once again, we have some clues that we have networking data where the crash is occurring. Obviously, the next and most important question is where in the system is it crashing? And we can look at the backtrace in the LR register to give us hints on that. So let's just do that. Let's go to the exact addresses in memory where the crash is occurring. Well, lucky for us, we find ourselves inside memcopy. And not only do we find ourselves inside of memcopy, but the exact line of code which it's crashed on, it is trying to take the data in R3 and store it at the address located in R0. Well, this fully explains why the system crashed. R0 has an invalid address in it that came from our payload, and it's attempting to store the first byte of the networking payload into that address. So this is obviously extremely interesting. But I don't know for you, the last time I opened up any commercial Linux application, memcopy was called more than once. So this is not enough. Sometimes memcopy is called hundreds of times. So what is the exact code path that triggered this crash? Well, we can use the LR register to help us figure that out. In ARM, the LR register points to the instruction that's going to be executed after a function call. So to actually know what function was called, we need to look one instruction before the address being pointed to by the LR register. In doing so, we can see a function called scnet_moved. Thank you again for leaving the symbols in. It was extremely useful. If we dig into this scnet_move function, it's actually just a wrapper for memcopy. And this becomes a place to start as far as understanding why this vulnerability exists. And if we continue down this path and we use the I2D compilers and a little bit of intuition, we can actually very easily statically analyze this bug and figure out why it's there. So I've renamed some variables here to help this be a little simpler to see, but what we have is we have a buffer which I've named source. And that buffer is being used to read data off the wire through a socket function. That buffer is hard-coded to be 1732 bytes, both in size and what it is to read off the network. And then after it's reading that off the network, it stores that in a variable, and I've renamed that size. So I want to point out for a second that this in itself, there is no development flaw here. It's statically defined. It's ensuring that it doesn't read more than 1732 bytes. This is perfectly fine code. However, if we continue to look at this code, we'll see a second buffer which I've named destination, which is allocated using the Linux packet alloc function to 1476 bytes. Again, if you didn't fall asleep in the beginning of the presentation, that number might mean something to you. That is the number that is the acceptable amount of bytes which is expected in a BACnet packet. However, it doesn't match the 1732 from the other buffer. Those experienced with vulnerability research and exploitation probably see where I'm going with this. There's a further call down the line where that scnet_move function is called, and it uses both those buffers, but it hasn't validated that it's the same size. And hence, we have a buffer overflow. But now I'll step back and remind you that I said just sending that large packet did not crash the device. In fact, sending 2 of the large packets didn't crash the device. It took 97. So what's that all about? Well, the interesting thing is the large packet triggers a buffer overflow. It overflows a section of memory where an address is being stored for a future memcopy. So what we've overwritten is that address, hence why it was stored in R0 in the beginning. So in order to exercise this vulnerability, it took 97 more packets before it tried to access that address. And So what we have is we have the initial packet, which overwrites a section of memory because of the buffer overflow, and 97 packets later, it takes that data and tries to write it to that address. And we have a typical write what where condition. This is really promising for us as vulnerability researchers because this means that exploitation is highly likely. Well, now that we've analyzed this statically and we think that we have something worth going forward on, we'd really like the ability to dynamically debug the system. Anyone that has done this type of work before, static analysis is great, but dynamic analysis really makes it a lot simpler. So, as expected, we compiled GDB server for the correct architecture of our device, plopped it on there, and started to debug, except for we instantly had a crash. And as you can see, this has been heavily redacted at the request of the vendor, but what you have going on here is there's a watchdog error which occurs because we've triggered a watchdog timer and the system reboots. For those not familiar, in ICS systems, watchdog timers are extremely common. They're used so that if the system stalls in any way, because these are critical systems, it takes some action in order to ensure that the system doesn't stay down. In this instance, the system reboots. However, it's a bit of a problem if you're trying to dynamically debug the system. Well, because the error messages were left in and because symbols were left in, it was actually very easy to track down this line of code. As you can see here, there are, I think it's about three counters which are being decremented by 5. So when the counters hit 0, it triggers the watchdog timer and it trips and the device reboots. Well, this is not a hard problem for us to fix as reverse engineers. We will just simply binary patch this binary. So we take the 5, we change it to 0, and now as far as the system is concerned, it still executes that line of code and decrements the value, but it decrements it by 0. As you can see on the right-hand side of the screen, even IDA now removes that line. It's not that it's not there, it's just ineffective. So thinking that we're pretty smart, we reload this back onto the system and we start debugging. And of course it starts to work until exactly 3 minutes later. And 3 minutes later, the system reboots itself again. Now, at this point, Mark's pretty agitated because he thought he already fixed the problem. So now we're looking and trying to figure out why the heck did the system reboot. Well, unfortunately, we forgot that in ICS systems, there's generally a hardware watchdog timer as well. And this hardware watchdog timer was set in boot, as you can see on the UART screen here, to 180 seconds or 3 minutes. So, how do we get past this? Well, if there's a hardware watchdog timer, that means the software on the system has to kick that watchdog timer. Well, in this instance, the developers, for all of their functions, exported the functions of the SO files, which means that all we had to do was use their code to kick the watchdog. So we wrote a small C program. We compiled the program for the device to execute those functions, and then set it to run on boot up. And so when the system boot up, it called our watchdog kicker, and it always kicked the dog. A combination of this hardware watchdog fix and the binary patch, and we were able to effectively remove the watchdog as a requirement for debugging, and we were on our way. Now that was a short tangent, but I thought it was worthwhile. So let's get back to the job at hand. We want to write an exploit for this system. So where are we at? Well, we have a broadcast packet with a payload of 1,732 bytes. By sending that packet, we can trigger a buffer overflow. That buffer overflow by itself does not crash the system. In fact, it takes another 97 packets to cause the crash. But when we cause the crash, it manifests itself into a write what where condition. We know from our initial analysis that there is no ASLR enabled on the system, but we do know that NX or DEP is enabled. So the next step is we want execution control. And if we have a write what where condition, this question simply becomes, what do we want to write where? Well, considering that NX is enabled, we want to find a location in memory that is writable that would allow us to gain some control of execution. Lucky for us, there's something called the global offset table. This is native to Linux, and it's a table created at runtime, therefore it is usually writable. And simply speaking, it has a list of function names and addresses. When a function is called, it looks up the address for that function, and then it jumps to that section of memory. Well, since we have a write what where and we can write anywhere we want, hypothetically speaking, we could take something like malloc, change the address of malloc, and then when malloc was called, we would be able to jump to our section of code. This would gain us control of execution. But we also need to know what function do we want to overwrite. Now we know where we want to overwrite, but what do we want to overwrite? This is a multi-threaded application, and so we really want to make sure that we gain execution control as soon as possible after the vulnerability is triggered. If we go back to where we saw the vulnerability exist in the scnet move function, we can see approximately 20 to 30 assembly instructions later, we end up with a function called scdecode BACnet UDP. This becomes the ideal place for us to gain control of execution as fast as possible from when the vulnerability is triggered. With all that background, the next simple thing to do was to write our own code to execute. And for that, I'm going to turn this over to Mark.
Thanks, Doug. All right, well, before we could finish pwning this device, it's important that we step back and look at the resources we already had available. So to begin, if you're paying attention and haven't fallen asleep, you know that we have execution control in the system using the GOT override that Doug mentioned previously. Additionally, the developers were kind enough to leave netcat installed on the device. And this is your granddaddy's kind with the -E flag, so you knew this was going to be good. Lastly, we still control some memory on the heap from our initial buffer overflow, although a lot of it does get clobbered by the time we gain execution control. Okay, so that's all well and good. The next question we have to ask ourselves is, what do we want? A simple question, but as Mr. Gosling can attest to, sometimes you just gotta ask. Well, we decided to start pretty simple. We wanted root access, obviously, but ideally we also wanted persistence on the device across reboots. So the last questions we had to ask ourselves were, how do we get this? But more importantly, how do we get it easily? You'll soon see that we still had a very long road ahead of us, so we wanted something quick. Well, by looking back at what we already had available to us, a straightforward way to get root access would be to use the netcat already installed on the device to obtain a root shell, or a reverse shell. We could accomplish this hypothetically by putting some shellcode into that heap memory we control, and this shellcode would essentially store a netcat command for the reverse shell into R0 register, and then branch to the address of the system function in libc. The system function, as you may or may not know, executes the command stored in its first and only parameter, in this case a netcat reverse shell command stored in R0. This ultimately comes together to create what is commonly referred to as a return to libc style attack. And although this would not grant us persistence on its own, ultimately we could use our reverse shell in order to alter some of the startup scripts, and that would grant us persistence on the device. So that's all well and good, but if we actually take a look at the heap memory we control, we'll see that it's actually not so easy. So the memory we still have that we control on the heap is the 22 bytes you see in front of you. And particularly, we have the longest continuous chunk that we control is only 32 bytes long, highlighted there in red. Now, why is this a problem? Well, the reason being is that somehow in this 32 byte section, we had to fit all of our shellcode instructions and the command string for netcat, which on its own is 24 bytes. Using some very complex arithmetic, this leaves us with a grand total of 2 ARM instructions, which is simply not enough to do what we want. Now, I know some smart asses out there are probably thinking to themselves, just use thumb mode, you dingus, those instructions are half the length. But although this is a great idea, through trial and error, we discovered that thumb mode is actually not enabled on the processor on the device. So that's out. I'm gonna level with you guys here. At this point, we were stuck. I couldn't sleep. I couldn't eat. I even considered switching over to an IoT webcam. Things were looking very, very dark. But suddenly I was struck with some motivation. I thought to myself, if I could live off of chili chow cup of noodles, registered trademark, for 4 years, then this should be child's play. And then I got thinking some more. Child's play, children playing, children play hopscotch, memory hopscotch. That was the key. Now what the hell am I talking about? Well, when we started digging in further, we found that we don't have to just use the 32 continuous bytes. We could use any section of memory we control as long as it's at least 8 bytes long. This grants us 1 shell instruction and a jump to the next region of memory we control, or hop, if you will. So if we look back at the heap memory we control, you'll see 2 such regions that qualify. This effectively doubles the number of shellcode instructions we have from 2 to 4, which is great news. But we weren't out of the woods just quite yet. Unfortunately, ARM is actually very cheap with its immediate values as an understatement. In fact, it limits them to only a single byte each with optional 0 padding left or right. This meant that if we wanted to load the address of system into a register, it would take all 4 of our instructions, and that wasn't going to fly. Well, thankfully, we were able to use the address already located at R4 because it was pretty close to the address of system, so with a simple offset, we could get there. In the end, this resulted in shellcode that met our tight memory space requirements and granted us a reverse shell. But instead of explaining in detail how cool this all is, how about I just show you instead? So here we have a demo video of the reverse shell in action. On the right half of the screen, I hope you can read it, is the UART interface of the device. Now the first thing we're going to do is we're going to run ifconfig to find out that its IP address. So you can see there it ends in 7.14. Next, we're going to print out the first few lines of the device's startup script. This is just to prove that we are in fact in the Delta device, and you can see the copyright message there. Next, we're going to show that there's no instances of netcat already running on the device. As you can see, we'll refer to this later. Moving over to the attack machine on the left, we start up a netcat listener on port 9. This will capture a reverse shell. And on the same attack machine, we launch our exploit script, which leverages the vulnerability and launches the netcat command you see there. So once it's finished executing, we move back to the UART interface and show that there is in fact an instance of netcat now running that wasn't before. And it has the same command string. So far, so good. Okay, moving back to the netcat listener, which should have connected, we run ifconfig again, and the IP address match. Imagine that. And just to confirm, we do in fact have root access. Okay, that's great. Mission accomplished, right? We got root access to the system, everything's good. Wrong. Like a tenured physics professor, we don't know when to quit. I mean, after all, we wanted I/O control on the device. We're more interested in the HVAC systems, the access control, the pressure rooms that are being managed by this device. And root access does not grant us that on its own. We needed to keep digging. Our next strategy was to look at how the device natively handles controlling the I/O hardware and maybe get some of that code to work for us instead. So the first approach we tried is to look at the database files located on the device's file system. Now something that immediately jumped out at us here is that I had no idea what the hell I was looking at. This was too complicated. Well, the next thing we tried is to look at what happens in terms of packets sent when we try to change the I/O state from the touchscreen. And maybe we could replay some of those packets. Now those of you paying very close attention might notice that the structure of the packet is actually very similar to the database, and that I still have no idea what the hell I'm looking at. This was still too complicated. Well, the last thing we tried is hooking to the I/O control functions natively. And this turned out to be just right. Now, as Doug mentioned before, symbols being left in proved invaluable here because functions with names like CAN-IO write output immediately jumped out at us because we knew that the I/O modules were controlled through the CAN bus. Furthermore, through reverse engineering of these I/O control functions, we discovered that there was different ones dedicated to controlling each category of I/O hardware, and there were 6 such categories. You got your inputs, you got your outputs, and you got variables, and these can all be either analog or binary. Now, our first initial naive approach was to try and execute these functions from external C code like we did with the watchdog kicking code. But unfortunately, the handles to these hardware devices were trapped inside the program space allocated for the Delta's existing programming, and they simply couldn't be accessed from an external code. Somehow, we had to figure out how to insert our malicious code, whatever ended up being, inside the program space of the existing programming. Well, the solution ended up being something called LD preload. And for those that don't know, LD preload is a Linux environment variable. And its job is that any shared objects this variable points to are loaded first by the dynamic linker when a binary is executed. Now, this is not a new or novel idea. This is actually a pretty common approach for inserting code into an existing program's memory space, which is exactly what we wanted to do. So in our case, we used our persistence on the device to alter one of the startup scripts, have this variable point to our malware, and then get it inside the existing programming. Now that's all well and good, but how does this work mechanically? Well, let's begin by looking at the normal operation of the device. So in normal operation, the first thing that occurs is that the Delta programming will execute. Pretty straightforward. Once the dynamic linker starts doing its job, it loads the shared objects in the following order. First, the DAC tetra binary, which is the entry point. Then all the Delta proprietary shared objects. And finally, all the other miscellaneous libraries, like libc. Now, once the programming is actually running, you have an I/O polling thread that consistently runs in the background, and this is what calls those I/O control functions I mentioned earlier. So in this case, we're going to look at an example where it calls the function canIO write output in order to flip a relay. Okay? Now, how does our use of LD preload change all this? Well, as before, the Delta programming will execute, but now the dynamic linker loads our malicious binaries first before any of the other shared objects. This becomes important when that background thread is running, because now it loads it calls the function with the same signature in our malicious binary instead of the real one, because those symbols are loaded first. Better yet, through the use of a C function called dlsim, we're actually able to get a handle to the real function at runtime, which means we can sort of do a catch and release approach where we intercept the calls to these IO control functions, mess with them however we want, and pass it back to the real deal with the program being none the wiser. Okay, so this is all well and good. We had malware, we knew how to insert it, but the question is, where the hell do we put it? Well, here are our options. Now, this diagram is a very high-level overview of the startup routine for the Delta programming. And through some reversing, we discovered that our best approach would be to use the function highlighted in yellow, canIO init. The reason why is because, as Doug mentioned, or maybe not mentioned, I don't remember, is that this programming is all vastly multi-threaded. So in order to avoid race conditions or inconsistencies, we wanted a function that was called early in boot, called by a single thread, and only called once. And this function met all those criteria. Now, what does it look like once the malware is inserted here? Well, this is what it looks like. When this function is called, our malware spins up a thread that runs in the background, and it listens for a command sent by the attacker over the network. Based on the content of these commands, the malware intercepts the corresponding IO control function in order to control the device the attacker wants to influence. Now, I've sort of been doing a lot of hand waving about how we actually alter these parameters in order to get it to do its job. So why don't I dig into that a little bit? Now, although there's a whole array of IO control functions, they did share one key commonality that we were able to take advantage of. And that's the fact that the first parameter passed to them is a data structure that essentially just describes the hardware being managed or being controlled. So in this case, you see an output of it here through GDB, and highlighted in red is the device's ID, the first 4 bytes. And this is unique to each device. At a 12-byte offset, highlighted in blue, is the current state of the device, which is actually the most useful. In this case, we have 75 degrees Fahrenheit as a floating point value. And then at an arbitrary offset, you could also find a descriptive string of the device, which is also extremely useful, because this is how we know this device in particular is responsible for monitoring room temperature. Using this information is actually pretty straightforward to just alter the state stored in these data structures, pass it along, and then we have control of I/O. Okay, so now mission accomplished, right? We control the I/O, we got root access. Well, the answer is still no. The reason being is that our motto here at ATR, unofficially, is to overdo everything. And in that spirit, we decided to pimp out our malware with all kinds of premium features. First of which, you get automatic discovery of all the I/O devices. Sit back and relax as the malware does all the recon for you. Next, you actually get remote control of the malware through an interactive TCP session. My therapist told me that the most important key to a healthy relationship is two-way communication. Now, am I saying this malware will fix your marriage? Yes, that's exactly what I'm saying. Next, you can see the state of all the hardware in real time, so you can see exactly how much damage you're causing. Who said happiness couldn't be quantified? And last, but certainly not least, with a single command, you can revert the device to its original, unhacked state, wiping it of any traces that the malware was ever there. And if you call in the next 30 minutes, you can get all this and more for just 30,000 easy payments of $19.95. Taxes and shipping not included. And if you're still not convinced, be sure to check us both out at ICS Village, where you can see this bad boy in action. Now, we were getting pretty happy with our malware. Our baby was looking pretty good, but we're still missing one key premium feature, and that's a remote attack vector. Now, this looked pretty grim at first because, after all, we were using broadcast traffic, and that typically doesn't travel over the internet. But thankfully, a certain BACnet technology came to save the day, and that is BBMD, or BACnet IP Broadcast Management Device. A real tongue twister, but suffice it to say, it allows for the transmission of BACnet broadcast traffic, exactly the kind we're using, imagine that, over the internet between different networks. So on the diagram on the right, you can see 2 such BACnet networks, each having a BBMD. The way this works is that broadcast traffic intended for a foreign network is first sent to the source network's BBMD. This sends it to the destination network's BBMD, and its job is to rebroadcast it on the destination network. That's a bit of an aside, but how does this help us? Well, through testing, we found out that using this technology allows for our exploit to work entirely remotely. Now, let me repeat that. At the time that this slide was created, any EBMGR connected to the internet of its default network settings could be pwned 100% remotely using this exploit. This is all pretty scary stuff. But what's the actual impact? What can someone do with this? Well, for that, I'm going to hand it back to Doug.
Thanks. So, as Mark said, we confirmed that this would work 100% over the internet. Now, I know everyone in the room will agree with me that no one would ever connect these systems to the internet. That would be completely unreasonable. Oh, that's right. Shodan tells us a little bit differently. At the time that we created this slide, there was approximately 500 of these exact devices running firmware that was vulnerable to this connected worldwide. Because of the nature of this vulnerability and where it's found in the code, if we extrapolate out that other Delta devices likely have the same vulnerability, this number balloons up to 1,600 to 1,700 devices, give or take about 10% for known honeypots. So, as Mark said, in the spirit of overdoing things, we actually decided to build a fully functional HVAC unit controlled by a Delta system in order to demonstrate the effectiveness of this type of attack. So if you'll watch on the video, as we move to the back of this demo unit, you'll see all the components you would see in a real working HVAC system. You'll have valves, pumps, fans, etc. And this was actually created by a contract company that actually puts these systems into current data centers. So this is as accurate as we could possibly make it. The only thing that's not 100% accurate is we use cold water instead of a compressor because my boss would not pay $8,000 for a compressor. On this side, we have an enclosed miniature enclosed data center, again with all the normal HVAC components, a raised floor, and a server which generates heat. For a moment, I want to draw your attention to something that was just on the screen, the independent temperature sensor. The reason this is important is it's the only component that you would not find in real life, and it's there to we always know the true temperature in the data center regardless of what the Delta says. Then on top of the system, we've added some lights to just show the state of different devices and to indicate an alarm is active. Once again, the boss got annoyed at having a siren, so he forced us to turn it into a light. But this alarm would simply indicate whether an alarm's been triggered. This could be in the form of an audible siren, a light, or even email notifications. This just indicates whether an alarm has been sent or not. So if this is the system, an HVAC system that is cooling a data center, what would happen if we applied the research we did to this system? Well, let's take a look. Here on the left-hand side of the screen, you can see an attacker running the exploit script. In the top right is a picture-in-picture of the Delta controller. The attacker leverages the vulnerability to download the premium malware, which Mark was talking about, and a few other extra pictures, and the device reboots in order to implement the LD preload strategy, which Mark discussed. Now, when the device comes back up, we've been a little creative with the images to show that the device has been hacked, and we will also log into the system. I want to emphasize that logging into the system is not part of the attack. We are simply demonstrating what the screen would look like and to follow along. It is not needed for the trigger anything for the attack. So something the attacker might want to do is control outputs on the device. This is, as I said, the device's function is to turn outputs on and off. So what would it look like if an attacker started to modify these outputs using the premium malware? You can see in the bottom right-hand corner that the device will react accordingly. In the top right-hand corner, the Delta screen, you might take notice that it is not updating. This is because the attacker has the ability to choose to change or not change the screen. If they want the user to know that something is changing, they can change it. If they don't, it won't, providing this attacker with a lot of different attack scenarios. Now, on these type of devices, there are multiple types of outputs. There are analog and binary outputs. What you just saw was binary outputs. We either turn it on or off. Analog outputs require a specific value, a floating point value, like Mark was mentioning, of room temperature earlier. So here what we're going to see the attacker do is modify one of these values, and this time the attacker is going to choose to modify the Delta screen as well, just proving that we can do it either way. So we have the fan speed and we have the valve. And you'll notice once again that the components on the actual demo rig react as you would expect. So, and also, as a premium feature, we built in a reset command, which sets everything back to its initial state, now with the attacker still having persistence on the box. So controlling outputs is kind of fun. We can think of scenarios that we may be able to influence by controlling each individual output. But if you remember from the beginning of my presentation, the devices are designed to take data as input and react. So what if the attacker was to modify the data the system was ingesting, or the inputs? As you can see here, the attacker is going to change what the system is reading for temperature, from the real temperature to 30 and 40 degrees respectively. Now what happens in your house if the HVAC system thinks it's 30 degrees in the room? Well, it's not going to kick on, it's going to turn off, right? And you can monitor our independent temperature system on the bottom right-hand corner of the screen, and the temperature in the data center is starting to rise. And there's no alarms being triggered because the system thinks it's 30 degrees. Why would it trigger an alarm? There's nothing that's going on wrong. So this is just one small scenario of one purpose of these devices, an HVAC system in a data center, of the impact we might have. I don't know if anyone here manages a data center, but what would happen if your data center went unattended with no HVAC for a long period of time? I cannot imagine that it would be a positive effect on the system. So let's look at some of the other scenarios that are possible with control of an industrial control system like this. One of the interesting things about systems like this is they are used in a very wide variety of industries because they're used in commercial buildings. You're not going to find one at home, but you will find them in the different industries listed here. I'm going to take a moment to talk about just a couple. I'm going to look at healthcare, government, and education. Excuse me. Healthcare is an interesting, unique case because it's usually used for something called pressure rooms. For those that don't understand what that means, in a hospital setting, different rooms are kept at different pressure points in order to prevent disease from spreading. And it's not much. It's just a little bit difference here and a little bit difference there in order to protect things like the OR or quarantine areas. And if an attacker was to get into one of these systems, this is what it's used for, and to just set all the pressures to the same value and chose not to update the screen and not to allow any alarms to send, nobody would notice. It's not something you're going to feel going in a room that the pressure is different. All of a sudden, those diseases that were contained by one of these systems could easily spread throughout the hospital. Might sound slightly dramatic, but it's definitely possible in this scenario. If we move on to a different situation and think about government, through OSINT, we were actually able to pull up documents openly available on the internet to see that these systems are used for access control in some state government buildings. I don't think I have to explain too in depth what the impact would be if an attacker was able to open and close doors as they chose in certain pretty sensitive areas of buildings. And lastly, I want to talk about education just because I think it's fun when people ask me questions, why would I care if you change the HVAC in my kid's room? Well, you probably don't care. But one of the other avenues of attack on these systems is they're an entry point into the network. If I have 100% control of one of these devices and it's not isolated, which again is nothing we ever see in the real world, but if they're not isolated from other networks, this now becomes a point that we can leverage in order to get onto other systems. I don't know, maybe stream cameras from different rooms out to the attacker's terminal screen or other things like that. All of a sudden, you start to become slightly more concerned. So these are just an example of some uses in the industry. And because of this, and because that it's a true RCE over the internet, it was assigned a CVSS score of 9.8. Per McAfee's responsible disclosure policy, once we understood what we have, we reached out to the vendor. This was in late 2018. We assigned the CVE number, and we started working very closely with the vendor. The vendor was extremely responsive, and as of June of 2019, they have released a patch which fully mitigates this vulnerability. ATR has also tested the patch and can confirm that it is, in fact, effective. I'd like to take just a moment to highlight this because I think sometimes there's a problem in our industry with security researchers and vendors. Delta was extremely cooperative. It was wonderful to work with, and we were actually able to come up with a solution to help fix this problem. And I think this really needs to become the gold standard in the industry for security research. We need to do this type of research to find these type of bugs, and the vendors need to be receptive, just like Delta was, in order for us to be able to fix these problems before malicious attacks can be created. I hope we've demonstrated that the impact of these attacks can be pretty severe, and if they're not attended to, we can actually have a problem. So thank you, Delta, for your cooperation. So with that said, that concludes the technical part of our presentation. I thank you very much all for coming. If you have any questions, as long as the goons allow us to stay up here, we'll answer them, or please see us in the back. I believe that's where they're doing questions. So thank you.